So when we talked about the role of the hydrosphere the other day in transferring energy from place to place on a global scale, we mentioned the term latent heat. Okay? And we mentioned it in this context. We said latent heat is heat that can be carried by water vapor from one place to another. It is essentially thermal energy that is stored in the vaporous state, okay, of water vapor, and then it's released when it condenses, right? That was essentially the context that we had talked about. And today we're going to look at that in a bit more detail. Okay? Latent heat isn't just heat that is held by water vapor. There's also latent heat in liquid water. Latent heat is really potential thermal energy. Okay? We know about kinetic mechanical energy, we know about potential mechanical energy, okay, like gravitational and that kind of stuff, but there's also potential thermal and kinetic thermal energy. Right? Kinetic thermal energy is measured by the speed at which molecules or particles are moving. That can be measured by temperature by a thermometer. Okay? Now, a thermometer measures that by having the energy of those particles hitting the thermometer, transferring energy to the thermometer and thus the liquid inside, causing it to heat up and expand. Okay? So we can only actually measure with a thermometer kinetic thermal energy. We cannot measure potential thermal energy with a thermometer. Right? Potential thermal energy has to do with the state of matter. Right? So it doesn't change until the state changes. Right? Because it has to do with not how fast the particles are moving, but how far apart they are. In a solid, particles are generally, water being an exception, but generally closer together. Okay? And so they can't get any closer together. So solids essentially have no latent heat. The particles cannot move any closer together. But when I melt a solid, let's say ice, the particles, the substance becomes a liquid and the particles move further apart. That's why a liquid can assume the shape of its container. Right? The particles can switch around, they can move and change places, and so thus it flows. A solid obviously doesn't flow, okay, but a liquid can. If I continue to heat that liquid, the particles move faster and faster and faster, increasing their kinetic thermal energy, but I get to a point where in that state the particles simply cannot move any faster. So they have to move further apart again. And that's what happens when a liquid turns into a gas. Right? They move apart again and gain even more potential thermal energy or latent heat. Okay? The opposite is true when we condense a gas. So if water vapor condenses, it releases all of that energy that it gained when the particles moved apart because they move back together. Okay? It's the same as if a roller coaster went down a hill. It's going to convert its potential energy into kinetic. Okay? And like push the particles closer together, they lose the energy they had when they were further apart. Everybody okay with that idea? Okay. So all substances generally have a heating curve that looks like this one. This is water's heating curve, but they all are generally a similar shape. Okay? There's the part of the curve, like down here, where the material is in its solid form. And if I heat it up and heat it up and heat it up, eventually it will melt. Okay? Now, weird thing about all substances is that unlike mechanical energy, where potential and kinetic can change at the same time, in thermal energy they can't. Only one can change at a time. So if I have a block of ice and I start warming it up, it doesn't melt right away. First, it has to get to zero. So I can change the kinetic thermal energy until I get to its melting point. Then the kinetic thermal energy will stop changing and the ice will melt. Through the entire melting process, the temperature stays at zero until all the ice is melted. Okay? Once all the ice is melted, then the water will start to warm up and the temperature will start changing again because now all the potential energy is done. Okay? I'll continue to heat that up until it gets to 100 and then the temperature will flatten again. Okay? The temperature won't change until all the liquid water has evaporated into steam. And then if I keep adding energy, the steam will get hotter. Okay? But only one happens at a time. I'm either changing the state or I'm changing the temperature. In other words, I'm either changing the kinetic thermal energy or the potential thermal energy, but never both at the same time. Okay? Everybody all right with that idea? So that's why our heating curve for water looks like this. Okay, so if I start down here at the bottom of this graph at minus 25 degrees Celsius, water is in its solid state, ice. If I add energy, okay, the ice will get warmer. It won't melt. It'll get warmer. It won't melt until it gets to 0 degrees Celsius. And then at that point, the temperature stops changing. I'm still adding energy, okay, because on the bottom of this graph is heat added, or energy, okay, and on the y-axis here is temperature. So you can see the temperature doesn't change, but I'm still adding energy. That's because now I'm changing the potential thermal energy and thus the state of the ice. It's melting. Once I get to that melted part and all the ice is melted, if I keep adding energy, the water will get hotter and hotter and hotter, okay, and it'll, sorry, it's got to be a solid line. Okay? It will get to 100 degrees Celsius, okay, along this line here. Once it gets to 100, if I keep adding energy, it stays at 100. I mean, if you've ever boiled water, this is true. Okay? If you had a thermometer in the boiling water, once you get it to boil, it stops. Okay? It just does not change temperature anymore. Liquid water, okay, at least here, boils at about 97.7 degrees, okay, something like that at this altitude. Okay? So it'll just stay at that temperature until all of the water is evaporated. Okay? Now, if you have like a sealed container where the steam couldn't escape, once it all turns to steam, the steam will start getting hotter. Okay? And that would be, okay, so this would be the evaporative part. Okay? And then once I had the vapor, okay, then the vapor would start heating up. Okay? Everybody all right with how that works? Okay. Yesterday, we learned a formula that calculates how much energy is involved in changing the temperature, or kinetic thermal energy, of a material. What was it? What was the formula we learned yesterday? E equals mc delta T. Okay, we can use E equals mc delta T in 3 places on this graph. Okay? What are the 3 places where I can use E equals mc delta T to calculate the amount of energy added?
Is it the melting point, the boiling point,
Actually, these are the 2 places here. The dotted lines are the 2 places I can't use it because what's the temperature change in those parts?
Oh,
0. Okay, so if I use it there, I'm going to get that the kinetic thermal energy isn't changing, which is totally true. In those 2 parts, it's not. But in these parts, here, here, and here, there is a delta T. So I could use that formula in those 3 places to calculate the amount of energy that would be required to heat either ice, water, or vapor and change its temperature. Okay? So down here, in the part where I would be using, or figuring out how much energy would be needed to change the temperature of ice, I'd go E equals mc delta T, and as long as I used the C for ice, I'd be able to calculate how much energy this required. Similarly, in this part right here, I would also use E equals mc delta T. Okay, but I'd have to use the C for water, 4.2. And similarly, right here, I could use E equals mc delta T. So anywhere where the temperature is changing, I can use that formula. Now, as I just said, that formula is not going to work when ice is melting or water is freezing, or water is evaporating or steam is condensing. I can't use it in those 2 places because it involves change in temperature. Energy is being added here, but not kinetic, only potential. Right? So I need formulas that can calculate my latent heat. That's what goes on in these 2 parts. okay, is the latent heat, okay, is changing. The potential thermal energy is changing. So, there are two kinds of latent heat. There is the latent heat of fusion, okay, which involves melting and freezing. And there is the latent heat of vaporization, which involves evaporation and condensation. Okay? So the process of liquid and gas and the process of solid and liquid. Everyone with me so far? Okay. Now, if we look at this graph, just from a, like, reading a graph standpoint, which state change involves more energy? Melting or evaporating? Evaporating, like a lot more. Okay? The evaporation phase of water's heating curve is by far the most energy intensive part of the curve. Okay? Changing water from a liquid to a gas requires a ton of energy. Okay? In fact, it requires 2,260 joules for every gram of water, for every milliliter of water to evaporate. Okay? Is that a lot of energy? Okay? By comparison, to melt ice only requires 333 joules per gram. Okay? Now, that's still a lot. I mean, think about if you've ever made a snowball in your bare hands. Okay? Like if your hands are just out bare in the air and it's cold outside, it's not so bad. I mean, your hands get cold eventually, but it's not terrible. But as soon as you pick up a bunch of snow and start making a snowball, do your hands get cold really fast? Why? Well, it shouldn't be. The snow in the air should be about the same temperature. I mean, if it's below zero, right? It's below zero, like let's say it's -2, the snow should be about -2.
The snow's taking the energy.
Yeah, I mean, first off, the snow is colder than your hands are, so it's going to take thermal energy because of the second law of thermodynamics. But once you heat that ice, that snow, to 0 degrees Celsius, it starts to change state. And for every gram of the snow that melts in your hands lose 333 joules of energy. Okay? That's why as soon as you start melting snow in your hands get cold way faster. Okay? Just to have your hands out in the cold air takes very little energy away. Okay? But when you're changing the state of the ice, it takes a lot more. Just a question. Yeah. Okay, is that making some sense? All right, so this number here we call the latent heat of fusion, and this one we call the latent heat of vaporization. They're the numbers, okay? They're kind of like the specific heat capacities, but they're for changes in state instead. So you will never have to memorize those numbers. They will always be on your formula sheet or test. Okay, they're actually on the back of your periodic table in the data section. So if we're melting something or if it's freezing from liquid to gas, the number is 333 joules per gram. So when liquid freezes into solid, it gives off 333 joules for every gram. Okay? But to melt it, it goes the other way. It would have to take in 333 joules for every gram. Okay? So the formula that we use to calculate how much energy is involved in this step is right here. The energy equals the mass in grams times the latent heat of fusion, which is 333 joules per gram. Okay? You're never going to have to manipulate that formula. You're always going to use it in that form. Okay? So all you have to do is take the mass and multiply it by 333. You're done. Super easy. Okay? All right, so how much heat would be required to melt 3 grams of ice cubes? 999 joules. Okay, I just take that 3, I multiply it by 333, and I get 999 joules. Okay, and for vaporization, it works exactly the same. I just use a different number. Okay, instead of 333, now I use 2,260. Okay, so if I have 1 gram of liquid water at 100 degrees Celsius and I want to evaporate it into water vapor, I will need to add 2,260 joules of energy to it. Okay? Everybody with me on that? So the formula for that part, okay, for this part right here, is E equals M, mass again in grams, times LV. This number is LV, 2,260 joules per gram. So, does that mean I could ask you to calculate how much energy would be required to take ice at minus 25, and let's say it's 200 grams. Say I have 200 grams of ice at minus 25, and I want to turn it into water vapor at 125. Could you calculate how much energy that would require? You absolutely could. Okay. For this part of the graph right here, you'd use E equals MC delta T. Okay? So I'd have my M, 200 grams, times the specific heat capacity of ice, 2.116, times, what would be the temperature change if I'm going from minus, if I'm starting from the bottom here? Nope. The total change would be 150, yes, but I'm only changing the temperature of the ice by 25. That's the trick. That happens a lot, actually, is people end up putting in the whole temperature change for the whole thing for each step. Well, remember, each step, I can only heat ice to 0. I can't heat ice to 125, right? So I'm only going to be heating the ice for this part here. So it would be 200 times 2.116 times 25 degrees, right? Then for this part here, I'd use E equals MLF. And I'd just go 200 grams times 333. And then for this part here, I'd use E equals MC delta T. So I'd go 200, and now that I have liquid water, it would be times 4.2. And what would the temperature change be for this part? 100 degrees. I'm going from 0 to 100. Okay, so it would be 100 degrees. And then for this part here, I'd use E equals MLV, 200 grams times 2,260 joules. And then for this part here, I'm heating it up again. There's a temperature change. So I'd use the formula that has temperature change in it. 200 times the specific heat capacity of steam, which is 2.02, times another 25 degrees. Then you would just add them all up, exactly. Okay? You will have a question like that on your unit exam. We're going to go over that today and Monday. Okay? But there will be one on there like that. It won't be from ice to steam, because that just takes too long. Okay? It'd probably just be like 3 steps, and maybe like liquid water to steam, or ice to liquid water, or something like that. Okay? It wouldn't be as much there. All right. Write this one down. We're going to walk through it together here. Okay. First step in doing a latent heat problem like this one is to draw out roughly the heating curve of water. Okay, that's this diagram here. Right? So I don't have to make it pretty, I'm just going to do this. Okay? This way I can figure out what steps I need to do. Okay? So in order to do that, I mark the starting point and the ending point of the question. So this question is asking me how much energy is required to heat 250 grams of ice at minus 15. Okay, so ice at minus 15 is here. Okay, because this would be melting at 0. Okay, so this would be 0 degrees, and this would be 100 degrees here. All right, so I would be starting here, and I'm going to steam at 150, which means I'm ending up here. How many steps are there going to be? Okay, so I'm starting with ice. I've got to heat the ice to what temperature? 0. That's step 1. Okay, so this would be my first step. What's happening here? The ice is melting. That's step 2. Once I've melted the ice, then I've got to do this. What's happening here? I'm heating up the water. That's step 3. Okay, then there's this. What's happening here? I'm evaporating the water. That's step 4. Okay, and then here, the vapor is heating up. I'm heating the steam. 5 steps. It's as big as the question can be. 5 steps is the most steps a question can have. All right, so once I've identified the steps, then I need to write down what the steps are and calculate the numbers for each step. Okay, so step 1, we said, is heating the ice to 0 degrees Celsius from 15 degrees Celsius. So what formula would I use to calculate how much energy that would require? I would use E equals mc delta T because there's a temperature change. All right, so for this particular question then, my numbers will be 250 grams. In fact, that'll be the number for M everywhere at each step, okay, times the specific heat capacity of ice, which is 2.116, times the temperature change. How much am I changing the temperature by? 15 degrees. Okay. So 250 times 2.116 times 15. All right, so that's going to require 7,935 joules. Okay. Now, step 2. Okay. In step 2, we're melting the ice. What's the temperature change during step 2? 0. So can I use mc delta T? No. Okay, because it'll tell me that no energy was required, and that's not true. So what formula am I going to use? No, there's no LT, but E equals ML, it's an F. It looks like a T, yeah. Okay, so E equals MLF. So mass times the latent heat of fusion. Okay, that's what we use for melting and freezing. Okay, so that's going to be 250 grams times LF, which is 333 joules per gram. So 83,250 joules. Okay, what am I doing in step 3? So So I start step 3 with water, liquid water at 0 degrees, and I'm going for water at 100. So what formula am I going to use? I'm going to use MC delta T. The temperature's changing again. Okay. Anywhere where the temperature is going to change, I'm going to use the formula that has temperature change as part of it. So 250 grams times. Now that it's liquid water, I have to use the specific heat capacity of liquid water. Okay? And I'm changing the temperature from 0 to 100. So 100 degrees Celsius. All right, so that takes 105,000 joules. Okay, when I'm done step 3, I have boiling water. Okay, I have liquid water at 100 degrees Celsius. What's going to happen to it? It's going to evaporate. Okay, so that's step 4. During step 4, there is no temperature change. So what formula will I use to calculate how much energy would be involved in step 4? Not MLF, but MLV. Yeah, I have to use the one for vaporization because now I'm vaporizing the water, right? I use MLF for freezing. Okay, I use MLV for vaporizing. Okay, does that make sense to everybody? So, E equals MLV. 250 grams, because the mass of the water doesn't change. It doesn't matter what state it's in. That's how much water I have. Okay, times 2,260 joules per gram. That's LV. Okay, 2,260 joules is LV, just like 9.81 is G. Okay, it's always the same number. Okay, 565,000 joules. It is more than the other 3 parts combined and multiplied by 3, almost. Okay, this is by far the most energy consuming part of the heating curve of water. Okay, so 565,000 joules. Okay, after step 4, I now have water vapor at 100 degrees Celsius. If I keep adding heat, it's going to get warmer. Its temperature is going to change. So what formula do I use? MC delta T. Okay, and I plug in 250 grams, because that doesn't change. Okay, now it's steam, so I need to put in the specific heat capacity of steam, which is 2.02 joules per gram degree Celsius, and I'm heating it to 150, so what's my temperature change? 50. All right, that's 25,250. Joules. Okay, so basically every other step is MC delta T. Okay, anywhere where the line is going up is MC delta T. Anywhere where the line is flat is MLF or MLV. If it's at 100, it's LV. If it's at 0, it's LF. Okay, just little things to remember. Okay? Otherwise, you don't have to manipulate anything. You just have to plug in numbers. Okay? But if I gave you a question like this that only had 3 steps, it would be an 8-mark question. Okay? Because I give you a mark for this. I give you 2 marks, 2 marks, 2 marks, final answer, which we haven't done, 1 mark. Okay, and none of these steps are terribly difficult. Like, they don't involve you having to do any algebra or anything like that. You're just plugging numbers into your calculator. All right, so my last step is I need a total. So I've got to add all these numbers together. Okay, so okay, so this is going to require 786,435 joules. Okay, 565 of which were to evaporate the water. Okay, so that vaporization phase represents a huge amount of water. That's why latent heat is such a good way of transferring large amounts of energy on a global scale. Okay. All right. Questions on how that heating curve works? Okay. All right. I'd like you guys to try questions 1 to 4. Okay? Write down what you think the answer is to those questions. You might need a couple of sentences. Okay? Write down an explanation kind of answer for those 4 questions. Okay? They're in your digital workbook if you're having trouble reading them on there. Okay? Yeah. And we're going to go over them here in a little bit. Why does putting ice cubes in your drink keep it cold? Besides the fact that ice is obviously colder, at least at first, than your drink.
Because the heat in the water goes into the ice.
Right, the heat from the water goes into the ice. And when you first put the ice in, it's probably about minus 15 degrees Celsius. But putting the ice in your drink, even if your drink is fairly cold, okay, if it's already like below 10 degrees Celsius, the first thing that happens is the ice very quickly gets to 0. Okay, now, as the ice gets to 0, okay, the drink is still not at 0, and nature doesn't like an imbalance. But the ice it can't get any warmer. The ice is at its melting point now. It's at 0 degrees Celsius. But your drink keeps getting colder. Where's the energy going? Yeah, it's melting the ice cube. And this is the part that actually keeps your drink the most cold, or cools it the most, is because for every gram of ice that melts in your drink loses 333 joules of energy. Okay, that gets it cold and keeps it cold, okay, for quite a while. Ice can absorb a fair amount of energy. Okay? I mean, it's why we fill a cooler with ice and not cold water. Okay, I mean, that's kind of the next question, or question number 4. What's better at keeping food in a cooler cold? 10 kilograms of ice or 10 kilograms of liquid water at 0 degrees Celsius? Ice. The water is already melted. Okay? The ice still it's already at 0, but it can still absorb 333 joules of energy for every gram that's in there, where the water can't. The water's just going to get warmer. Okay? The ice isn't going to get warmer until it melts, and it's going to take a lot of energy to melt it all. That's why we do that. Okay? That and everything will get soggy if we just fill it with ice. But I mean, eventually, or with water. But eventually, the ice turns to water anyway. Okay? The advantage of the ice is that it's lower on the curve, right? This is our heating curve. Okay? If I just fill a cooler with water, okay, I'm starting here if I fill the cooler with water. But if I fill the cooler with ice, I'm starting here. That gives me more of the curve to absorb energy, and it's going to do a better job of it. Okay? So that's kind of questions 1 and 4. How does sweat work? How does sweat keep you cool? It's got to be good for something. It's just, it's disgusting to be soaked in sweat, smelly. Okay. How does it keep us cold?
The heat is absorbed by the sweat and then it evaporates off us, taking thermal energy with it.
Exactly. For every gram of sweat that evaporates from your body, 2,260 joules of energy from your body go with it. Okay? That's why if you're just laying in the sun and you're just sweating, okay, you feel really, really hot. But if you just get up and walk around, you increase the rate at which the sweat evaporates and you feel cooler. Even though you're more active, you're going to feel cooler just because you're getting the water to evaporate. That's why if you've got a fan here and you're not standing in the path of the air, you feel really hot. Then the fan rotates around and the air gets on and suddenly you feel so much better. It's increasing the rate of evaporation and you feel cooler. It's not that the temperature is any cooler. A fan doesn't blow cold air. A fan just moves the ambient air around. But you feel cooler because it's making the water on your skin evaporate faster, okay, helping you to cool down. Right? This is also why we dress in layers in the wintertime. If you leave on all of your layers and you go outside and you shovel the driveway or something like that, you're going to get all sweaty. Okay? And then, let's say you locked yourself out of the house, so you can't get back in. You are now soaking wet and it's freezing cold outside. That water is still going to evaporate. And as it evaporates, it's going to take the energy from you and you are going to get hypothermic in a hurry. Okay? That's why you dress in layers. As you start to get warm, peel the layers off. Okay? That way you don't overheat, the layers stay dry. Okay? Worst case scenario, whatever shirt was next to your body, you switch it out for a dry one and put the rest of the layers back on, and now you've got nice dry layers and you won't get hypothermia. Okay? Does that sort of make sense? Okay? That's the reason why we do that. The worst thing you can do in cold weather is sweat. Okay? That's how wind chill works. Okay? Water evaporating from your skin amplifies the effect of temperature. Okay? All right. So is a person who sweats a lot cooling their body better than someone who like just perspires a little? Nope. Okay? In fact, you only need a very thin layer of perspiration for sweat to be effective. Everybody sweats differently. Okay? But somebody who drips with sweat after going up one flight of stairs is not going to cool their body better than someone who just perspires. Okay? They just sweat more. Okay? But it doesn't necessarily make it better or worse, okay, in terms of its cooling ability. All right, we will talk more about that on Monday. Have a good weekend. Apparently, you'll need to try and stay dry because it's going to rain a lot. Which we need, so it's green grass. Green grass. Green is good. We only get to see it 3 months of the year. Enjoy it while it's here.